Okay, so what we did, we identified that in this part of the course, we'll be dealing with vectors. And in vectors, we said that there are two forms. There is the rectangular form, which is the number will be in this format, a plus j b, where a is the real part and b is the imaginary, with j, as we identified, is the root of -1, the complex number or the imaginary number. And also we said that we can write the same thing in a polar format. So it's z angle of theta. So you have a magnitude and you will have an angle. So we could have it in rectangular format, or we could have it in the polar format. Now, as we have seen in circuit, we apply KCL, KVL nodal. So the electrical part is concentrating on setting the equations, either in terms of currents, like in KCL and KVL, or in terms of voltages, if we are talking about nodal analysis. Then after that, we have to deal with these equations. We have to do a lot of mathematical manipulations to find the voltages and the currents of interest. So now, in this part of the course, we will not deal with the scalars, but we will deal with vectors. So we need to know how to do mathematical manipulations in these vectors, and that's what we'll be concentrating. Now, when we want to add or subtract, then the numbers has to be in rectangular format. You cannot add and subtract numbers in the polar format. So, for example, if you have 1 plus j2, this is one number, this is another number, 2 minus j4, and then I want to add these two numbers, so I add the real to the real and the imaginary to the imaginary, minus j2. So this is how we deal with it. If we have them in this format, you cannot. So if your values are given in polar, then you have to convert them first to rectangular, and then you add and subtract. Now, when it comes to multiplication, is the opposite. If we multiply two numbers, let's say z1 equal to magnitude z1, angle theta 1, and z2 has a magnitude of z2 and angle of theta 2. When we multiply them, we will multiply the magnitude with each other, as here, and then we will add the angles. Okay? Now, if we divide the real values or the magnitude with each other and subtract the angles. So in conclusion here, if we are doing mathematical manipulation, if you are doing addition, subtraction, do it in the rectangular format. If you are doing multiplication and division, then you can do it in the polar format. But however, these two operations can also be done in the rectangular format. Let me give you an example. Let me take these two examples, or a plus jb times c plus jd. I can still multiply these two numbers. This is easier, but still I can do that. So multiply a with c. So a times c, a times jd plus a times jd. So this is the first thing, multiply a with the whole bracket. Then j times b, so this is plus j b times c, plus j times j square, which is -1, and b times d. So I can do the multiplication when we are in the rectangular format, and also we can do the multiplication, but even it is longer and harder in division as well. So for example, if we have 1 plus j2 divided by 1 plus j, and I want to do this division, how we do that? Now, one way is to convert, and this is the one I will advise you to do. Convert everything into polar, and becomes very straightforward. The division is straightforward. You can use the software I showed you yesterday, so it becomes very trivial. And then divide the magnitude, subtract the angle. Very straightforward. However, this is just for your information. We can still do this in rectangular format. How we do that? We multiply with something called the conjugate. What is a conjugate is the same number, but we change the sign of the imaginary part. So we multiply, and this is, we do that for the denominator. So we multiply by 1 minus j, divide by 1 minus j. So this is the conjugate of 1 plus j. So we multiply 1 minus j over 1 minus j. Now when we multiply this, we are multiplied by 1. So I'm not changing the number actually. Now we can multiply the numerator, but let's talk about the denominator here. So basically what we do, 1 times 1 is 1. 1 times minus j is minus j. J times 1 is plus j. J times j is minus 1. And there is a minus, so it becomes plus 1. So plus 1. Okay. I hate this format. I don't like it. Let me just go back to our format. Okay. Just bear with me. I am okay. I'll come back. Keep this. Let me just go back here. So basically here, this is plus. So this will cancel with this. So what will happen here when I multiply by the conjugate, I get rid of the imaginary part, and I will be dividing only by a real part. And this will become simple. 1 times 1 is 1. 1 times minus j is minus j. J2 times 1 is plus j2. J times j is minus 1. And there is a minus, so it's plus 1. 2 times plus 2. Okay, so here I divide by a real number. So when I divide by a real number, there is no imaginary, then it becomes very straightforward. So we can do it in the rectangular format still. However, as I said to you, I strongly recommend that we do it in the polar format. So this is summary of everything about the properties of how to deal with a complex number. So addition, it has to be in the rectangular format. When you add the number, so you add the real to the real, imaginary to the imaginary. Subtraction, again, it has to be in the rectangular format, so you subtract the real with the real, imaginary with imaginary. Very straightforward. Multiplication, as I said, it's recommended to do it in the polar, much easier. You multiply the numbers, the magnitude, and you add the angles. In the division, you divide the magnitude, subtract the angles. If you want to take the reciprocal or the inverse, so 1 over z, so it's magnitude 1 over r, and then this becomes minus phi. How this happened, I can explain. So this is 1, actually it's 1 angle of 0, divide by r angle of phi. So 1 over r, we divide the magnitude, and the angle, you subtract them. So it's 0 minus 5. So this is why it is like that. Square root, if I take the square root, it has to be done in the polar format. So basically, you take the square root. So if you take the square root of r angle of phi, so the magnitude, you take the square root of the magnitude, and for the angle, you divide by 2. Complex conjugate, this is what I just mentioned to you. In the complex conjugate, we change the angle of the imaginary part. Or you can also take the conjugate of the in the polar format, you change the angle of the sign of the angle. And this format, we don't use it actually, so don't worry about it. This is one format of the complex number. We use it in something called the Euler formula, but we will not use it in this course, so you don't worry about it. Now let's do some examples. And as I said, that's what you will be doing a lot. You will be doing a lot of math. So it's very, very important that you feel comfortable dealing with this. So for example, here you multiply 2 rectangular numbers, and then you subtract from this a polar number. This will be very, I mean, this is like the basics of the manipulation that you will be doing in this course. Or division and addition. You divide rectangular, you add to it a polar format. So let's do that slowly. So the first example is 5 plus j2. We multiply this with -1 plus j4. So these two numbers in rectangular form. I subtract this 5 minus 60. This could be like an outcome of a KCL or a KVL or any of mathematical manipulation. So start with multiply. I can multiply, as I said, multiplication is not a big deal. I can do the multiplication in rectangular format. 5 times -1 is -5. 5 times j4 is plus j20. j2 times -1 is minus j2. J times j is, this is plus, because plus times a plus is a plus. J times j is -1. 2 times 4 is 8. So -5 minus 8, so this becomes -13, plus j20 minus j2, so j18. So this is the outcome of this multiplication, -5 angle of 60. Now I have a number in rectangular format. I'm subtracting from that a number in the polar format. So this is the reason why I kept this in rectangular, because eventually I have to change this into rectangular. So if I change these two into polar, I will get a polar number. So at first I have to convert these two rectangular to a polar, multiply them in the polar format, and then convert them back into rectangular. So I thought that will be like saving some time. This will be faster. So I need to transfer this into polar format. So this is equal to -13 plus j18 minus. Now here you use the software 5 angle of 60, the software that I showed to you before. This is equal to 8 plus, sorry, it is 2.5 plus j 4.3. This is the conversion of this, which is basically 5 cosine 60 will give you this, plus j 5 sine 60 will give you that. So this is the two numbers now in rectangular format. So we'll take the real with the real, -13 minus 2.5. So this becomes -15.5. j18 minus j 4.3. So this is plus j 13.7. Okay, so this is in the final answer. I could keep this one as this, or I can change this into its equivalent polar format. It doesn't really matter. For the answers, you can keep it either in rectangular or in polar, unless I specify the format, but usually I don't. Okay, so now sometimes it's preferable or it will be needed to do this if I ask you to find the time domain representation, because the time domain will be a cosine omega t plus theta. So I need the a and the theta from the polar. I can't get it from the rectangular. So if I ask you what is the time domain output, then you have to convert everything into polar. And other than that, you don't need to do that. Okay, so let's do the other question, B. So here we have 10 plus J5, which is this one, the other example here. So it is mixed of everything almost, plus 3 angle of 40 divided by -3 plus J4 plus 10 angle of 30. Again, some math like this, ending up a formula with the mixed rectangular and polar, mixed addition with subtraction, with division, with multiplication. That's very, very normal. And that would be an outcome of your KCL, KVL nodal, etc. Okay, so let's do it one by one. So the first thing here we have in the numerator, we are adding two numbers, one in rectangular format and the other is in polar format. So the first thing we need to do here is we'll try to convert this into a polar format, sorry, into a rectangular format so that we can add these two numbers. So this becomes 10 plus J5 plus. Now we need to convert this. Now, as I said, you can use the software to do that. So this is 2.3 plus J 1.93 divided by minus 3 plus J4. You keep everything as it is. So you do it one at a time. Plus 10 angle of 30. So now we have real with real, imaginary with imaginary. So we add this with this. So this becomes equal to 12.3 plus J 6.93 divided by minus 3 plus J4 plus 10 angle of 30. So we are done with the first mathematical manipulation, which is the addition. So we converted this into rectangular. We add them. We have the number. Now we have a division. So as I said, in the division, it is better that you convert this into what? You convert this into these two numbers into polar format. So this becomes 12.3 plus J 6.93. This is equal to 14.12 angle of 29.4 divided by, same thing here, 5 angle of 126.87 plus 10 angle of 30. So now we have a division in polar. So I will divide the magnitude, subtract the angle. So what we will get here 2.824, and the angle will be minus 97.47 plus 10 angle of 30. Now I'm adding two numbers in polar format. I cannot do that. So I have to convert both numbers into rectangular format. Okay, so this number, the first one, becomes equal to minus 0.37 minus J 2.8. So we are done with this. Plus the other number, 10 angle of 30, is equal to 8.66 plus J5. So now we have these two numbers in rectangular format, real number with the real, imaginary with the imaginary, and we are done. So this is equal to 8.29 plus J 2.2, and this is your answer. As I said, if I didn't specify that I need you to convert this into time domain, you can keep it as such. So you have seen here there is a lot of math. So you have to be very comfortable. And as I said, one of the hints, it makes your life much easier, is to use the online uh, polar to rectangular converter. And you're lucky because you are working online. If you are in person, you are not allowed to use this. So this is a luxury that please use it and save your time, because in the exam, especially dealing with AC, you will not have a trouble with the circuit concepts. If you understand the midterm material, you will not have any trouble understanding this. However, you will have a trouble if you don't know how to deal with the math. You will get stuck. You will not be able to move. You will write the equations correctly and then you get stuck. So you have to be very familiar with this. Okay, now sometimes you have sources, different sources, and you want to add them. And you want to add them in the V1 is 20 cosine omega t minus 45, and V2 is equal to 10 sine omega t plus 60. So here, notice both have the same omega. It is giving as a symbolic. Okay, it could be given as a value, as a number. It doesn't really matter, because when we go from the time domain representation to the frequency or the phasor representation, sometimes it's called a frequency representation. We take out the frequency. We don't know the frequency anymore. It's not there, because we will have the thing is as a magnitude and as an angle. Okay, so now we want to do this addition, and this is one of the advantages of using the phasor representations, because adding this in time domain, it's not possible to do that. It will be very hard. If you want to do it, maybe you need to write a code to add the points one by one to get the signal. And when you get the signal, you will not be able to get the formula. You will get a signal, but you will not be able to get a formula. However, if you convert this into phasors, add the phasors together, convert it back into time domain, then you will get a nice, neat formula for the addition of these two cosine functions. So we need first to convert these two into phasors. So we have the first one as a cosine function. So this would equal to magnitude 20, angle of minus 45. That's it. So this is the cosine function. We take the magnitude and we take the angle. As I said, no frequency. Now the second one is a sine function. We said that our standard of this conversion based on one assumption that our signal is in cosine format, not in sine format. So first we have to convert this into cosine. So this is by adding minus 90. So this becomes 10 cosine omega t plus 60, the same angle that we have here, minus 90. So this becomes minus 30, and this equal to now 10 angle of minus 30. We are set now. We can start the addition. So your V1 plus V2 will equal to 20 angle of minus 45 plus 10 angle of minus 30. Now these two are in polar format. Now we'll go back to what we just learned. I'm trying to make the link slowly, because this is eventually what we'll be dealing with. This is the input to the circuit, but these are the math, the intermediate step. Okay, so now we need to go back to the property I just covered today, which is how to add two numbers. Now these two numbers are in polar format. We cannot do that. So first we have to convert these two numbers into rectangular format. So I will convert the first number, which is equal to 14.14. I really urge you to, after the class, to go back and to use the software I show it to you, or any other software as a matter of fact, and then try to do this addition or subtraction, division, multiplication. Make sure that you get the right number. Make sure that you are comfortable dealing with this math. J 14.14. So this is the first number plus. Now we'll do the second number, which is 8.66 minus J5. Okay, so now we have real, imaginary, imaginary. So we add the real. So this would become equal to 23.06 minus imaginary with the imaginary minus 19.14. Okay, now if we want to find the output in time domain, that's not sufficient. I have to convert this into polar, back to polar. So this is as polar 29.97, and the angle is equal to minus 39.7. Okay, so now we have the magnitude and the angle. Now I am ready to do what? I am ready now to find your V1 of t plus V2 of t as magnitude 29.97 cosine omega t minus 39.7. So this is the outcome of these two additions. So see, with this simple math, we will be able to do some mathematical operation that would be very difficult to do it without this conversion. Now, at this level, we have enough of math. Now, let's go from our math stand to the circuit stand and start to see things from the circuit perspective. Now, we have three passive elements in a circuit: resistor, inductor, and capacitor. And we have a source. The source will be in cosine function, sinusoidal, sine or cosine. Okay, and now we need to see, okay, how we will handle. So let's imagine that we have an AC circuit. Now we are talking about AC. So this could be, it's a black box here, but this could be like an R, inductor, capacitor, maybe another capacitor, another resistance, whatever is. So this is a combination of L1, R2, C1, C2. So we have a source. Now this source is a cosine function, but I am writing it now into polar format. So this is originally Vm cosine omega t plus theta V. And then I have a current coming out of this, Im. And this Im will have its own current. It will usually we'll see that only in certain specific case the angle of the current and the voltage will be the same, but we'll talk about that later on. But the general formula that the current will have a formula and the voltage have a formula. Now here everything will have certain Z, which has a different. Now how to find this Z is nothing but the Z, basically we divide the voltage by the current. This is called Ohm's law. Okay, divide the voltage by the current. So we'll take the voltage in the polar form because we are dividing. So we'll keep things in the polar format. The voltage and the angle divide by the current and the angle, divide the voltage by the current magnitude, subtract the angle, then you will get this. So basically this is your Z. Now this Z will have a name for it called impedance. We use the word resistance. Resistance in DC circuit. And still here for R. R will stay the same, it's resistance. But now we have a more general format that represent the combination of R, L, and C, and we will use for this the word impedance, not resistance anymore. And this impedance will be a vector as well. It will have a magnitude and it will have an angle. And here, because we are dividing the voltage by the current, the magnitude of Z is the same like the magnitude of R. For example, if you have an R, V, sorry, I and V, this is your I, we know that R is equal to V over I. The magnitude of the resistance is V over I, and actually R is just a magnitude. So here the same thing. The magnitude of Z is the magnitude of V divided by the magnitude of I. But here we have something else, which is the angle. We deal with an angle now. So Z is not anymore a scalar. Z, like anything in AC circuit, is a vector. Now, the unit of the impedance is ohms. It's the same as the units of the resistance. So although now we have more complicated circuit with R, L, and C, but still this Z, which has a magnitude and an angle, its unit is in ohms. So now this Z will have, I can change this into real and imaginary. Okay, so basically this magnitude, if I multiply by cosine theta, how to change from polar to rectangular, I will have an R. And if I multiply by J sine, I will get an X. So now your impedance has two components. The real part, we call it the resistive components, which is coming from the resistance part. So the resistance will give you always a real part. The real part in the impedance is coming from the resistance. Then we will have a plus, and actually there is could be a minus. It could be a plus or a minus J of X. So this imaginary part is called the reactive component. And this reactive component will come from either L and or C. So the L and the C will contribute only, as we will see, as we'll derive this together, to the imaginary part. But the R will always be the real part in your circuit. So if you don't have in your circuit any L or any C, then you will have only resistance. But once you start to have L and C, then you will have this imaginary part. And again, the Z and the theta Z that we have here, you can go back and forth between the R and the X. You can convert the R and the X to the Z. You can convert the Z to R and X. Same thing for the angle. Now let's work on every single item by itself. Let's see what is this Z if we have only an inductor? What is this Z if we have only a capacitor? I just mentioned here that the L and the C will contribute only to the imaginary part. But let's prove this. Let's see this and try to appreciate it more. So we'll start with the inductance, which is derived from the inductor. Okay, so I will have an inductor here with value of L, and I will have I, L, and then I will have V, L. And I want to find what is the impedance. What I will get if I divide V by IL, applies Ohm's law. What is the value of Z of the inductor? So now we are working in AC. So assume that your IL, your current, is equal to Im sine omega t plus certain angle theta. You could have it as a cosine. It doesn't really matter. Okay, now the one thing we know, the relation between the voltage and the current in the inductor. We know that VL is equal to L DIL by dt. This relation doesn't change if the circuit is DC or AC. This is always true. So I want to apply this. So this is equal to, take this is, there will be an L, take the derivative of this. So omega will be taken out of the derivative. So it becomes omega L. And this becomes equal to what? To uh, magnitude Im as it is here. So all these would become here. So just take omega outside the sign. We have the L and we have the Im. Now this becomes cosine. Cosine omega t plus theta. Okay. Now, in the previous example, I have shown to you if you want to find Z, I need to divide by the voltage by the current. But the voltage and the current has to be in the polar format, not in the time domain, not in the rectangular format. So I need to convert this and this into a current and a voltage, but they are in the polar format to find ZL. Okay, now this is sine, so I can convert this into cosine by having just minus 90. So this becomes Im cosine omega t plus theta minus 90. And this will equal to omega L Im as it is, cosine omega t plus theta, no change. There is a question here, let me see it. It says here, where did the di dt go? What did we derive? Okay, it didn't go anywhere. Actually, I'm trying to find the voltage. Okay, I know the current. I assume the current is equal to this, a sinusoidal. It could be sine or cosine, it doesn't really matter. Then the voltage is equal to LdI by dt. This is the relationship we derived before in the inductor. So basically, I took the derivative of the current, multiplied by L, I get this formula. So now I know the voltage and I know the current. So assume a current, sinusoidal, because we are working in a sinusoidal. So it could be a sine or a cosine, it doesn't really matter. So it has a magnitude, sine function, and an angle. So this is, and then I converted here to cosine by having minus 90 because I want to convert this into a polar format. The voltage is L times the derivative of the current, so we'll get this. Okay, now this will equal to a magnitude. Now, as a notation, in polar they use capital letter. Time domain they use small letter. So IL is equal to now, equal to Im as a magnitude, angle of theta minus 90. And from here, VL will equal to, this is the magnitude, omega L I M, angle of theta. Okay, we are set. Now I want to find this L. I want to convert it. Now remember, the L, the unit is Henry. We don't want to work with L. We want to work with what we call ZL, or the reactive component, or the reactance, or the impedance of the inductor. So this ZL is nothing but VL divided by IL, which is equal to, your VL is equal to this, omega L I m angle of theta divided by the current, which is I m angle of theta minus 90. Just divide the voltage by the current. Now the Im will cancel. Okay, so this will becomes equal to omega L, and the angle becomes equal to theta minus 90. So this would equal to omega L angle of 90. Okay. Now, this is in polar format. I can also say that your ZL in rectangular format are real and imaginary. What is the real? It is equal to omega L cosine 90 plus j omega L sine of 90. Omega L cosine 9, this is equal to 0, so this is equal to, and this is equal to 1. It's equal to j omega L. And this is a very important conclusion. So the inductor in AC analysis, it will be converted into an impedance. Its value is equal to j omega L. If let's go back here, we said that the inductor and the capacitor will contribute to the imaginary part only. It will not contribute the real part, and we have seen this, that ZL of the inductor is equal to j omega L. So what is omega? Omega is the frequency in your signal. So the frequency of your signal will actually dictate the impedance value. Let's go for the extreme. What if omega is equal to 0? Wait a second. But omega equal to 0, it means this is what? DC circuit. DC omega equal to 0. So in case of DC, omega is equal to 0. So it means that your ZL will equal to J times 0 times L, which is 0, which is what? Short circuit, which we already derived in the DC circuit. When we model the inductor in the DC circuit, we said it's a short circuit, and we derived that from the differential equation because the current doesn't change with time. So we said this di by d equal to 0, the voltage is equal to 0, an element has a voltage equal to 0, it means a short circuit. Now we can look it from a different angle, we get the same conclusion, that ZL, this is the general formula for the inductor, reactance or impedance equal to j omega L. And remember, this imaginary part, the unit is in ohm. L in Henry, but ZL is in ohm. So now when we apply the DC here, if we assume we have a DC, then basically omega equal to 0. There is no frequency. If omega is equal to 0, then this becomes equal to a short circuit, which we already derived before, which is make everything in sense. Now we'll go to the capacitor. We'll do the capacitor a bit faster. But before that, it's interesting to see the relationship between the voltage and the current in a waveform perspective. So when we look here, now we realize that the voltage has an angle of theta. So this is the angle of, so now this is called the phasor diagram. So I can, because it's a vector, so I can represent the magnitude of the vector as a magnitude and an angle. So this vector with an angle of theta and the magnitude of VL represent your voltage. Now, the current, as we have seen, and this is always the case, the current has a minus 90 with respect to the voltage. So always the current, we call the current lags the voltage. Okay, so the current is behind the voltage. So the current will have a 90-degree phase shift between. So whatever theta is, the current is always 90 degree. So if you go this or you go this way, the current will go or will always maintain this 90-degree phase shift in the inductor. If we look to the time domain, this is your VL and this is your IL, the blue line. You will see this 90-degree phase shift between them. Now, the voltage, still the voltage, so here when the voltage is actually at zero, the current is in the negative. So the voltage goes up, the current goes up, and this phase, now when the current reach the zero, the voltage will be somewhere here. So this is the 90 degree. Here, this shift here is the 90-degree between the voltage and the current. So they are not in phase, they are out of phase. And the phase difference between them, either you take, if you take two zeros, or you take the peak difference, it is 90-degree. When the voltage reach its peak value, the current is at zero. When the current reach the peak value, the current is, or the voltage will be somewhere much around zero. So here it is, the phase shift 90-degree between the voltage and the current. This is very interesting, and we say that the current lags. So what we call this is called the phasor diagram for any vector. Any vector, for example, I have a vector equal to angle 5, angle of 30. So I can represent this as a vector with a magnitude equal to 5 and an angle of the 30. If my vector, let's say, is equal to 10 angle of minus 15. So again, I will have, this is my reference. The positive x-axis is my reference. So I have a vector here, magnitude of 10 and angle of minus 15, and so on and so forth. So again, this is something very important to know, and it will show you the relationship between the voltages and the current, who is leading and who is lagging. We said that the current lags the voltage, or the voltage leads the current by 90 degree. I will stop here, and on Thursday I will continue for the capacitor and the resistance, and then we will put everything into one perspective, and that perspective is how, like, we'll have like a universal approach, how to approach the circuit in AC analysis. So we'll start this on Thursday after we understand the behavior of the inductor and the capacitor. So we'll stop here.